around the circumference in one period, squared. So we're left with G, mass of the Earth, over R is equal to 4 pi squared R squared over T squared. Now, what do we do next? We're just sort of playing around at the moment. I am actually doing a pseudo derivation of something. So what I'm going to do is I'm going to get the R's and the T's on one side, everything else on the other. So I have G, mass of the Earth, over 4 pi squared, so just moving it across the diagonal, equals R cubed over T squared. What this claims is, for things orbiting the Earth, that if I take the radius, the orbital radius cubed divided by how long it takes to go around once squared, it is going to be the same for every object orbiting the Earth. Or if we want to change the mass here to the mass of the Sun, then everything that's orbiting the Sun, if I look at the orbital radius cubed over the how long it takes to go around once squared, it's going to be the same for everything going around the Sun. And it comes out pretty darn close. This is Kepler's first or second law of motion. They're trying to keep track of which Kepler law is which. Now, it turns out that things don't actually travel in circular orbits, they travel in elliptical orbits. And as things travel in elliptical orbits, what's an ellipse? Close to it. So if I take 2 points and I have a string dangling between them, I take a pencil and I pull it so that the string is tight. And then I start moving it around so that the distance from this point to the pencil to that point is the same everywhere I am. Better drawn than this, I assume in your notes you will be flawless. You get what looks kind of like an oval. That's an ellipse. And one of other Kepler's laws is that objects travel in an ellipse where the Sun is at one of these 2 points here. And these are known as the plural is foci, or the Sun is at a focus. So the Sun would be here, the Earth travels around in this ellipse. So it's 2 of Kepler's laws, and the third Kepler law is that if you look at how far the Earth travels in a month, for example, or any time period. So let's say the Earth travels that far in a month. So it sweeps out that area. If we'll just set up a month, 30 days. If it sweeps out 30 days anywhere, the area is the same. Kepler spent all of his life coming up with these rules based upon the observations of planetary motion. Absolutely brilliant. And like Cruelty skit, he and Newton did not live at the same time. Kepler died a couple of decades before Newton was born. But just imagine, Kepler's 38 years into this, studying these charts very carefully, and he goes into a bar after a long day's work. Who does he meet but Newton? They get to talking about what they're doing. Kepler says, I've been working on this for 38 years. I think I've almost got it down to the rules of planetary motion. And Newton goes, oh, you got a couple hours? I can show you how to do it. All of this can be derived from Newton's laws. Now, afternoon's probably an exaggeration. Give him a day to learn calculus, and then the rest of it. And I don't know if I have the videos posted for 151. I might have them posted under chapter 6, where I go through the calculus derivation of it, just in case somebody's interested. But all of this comes from Newton's laws. The other cruelty joke in science related is the first person who came up with the radius of the Earth. The Egyptians, that was several thousand years ago. And the stick had to be perfectly upright, and had to be perfectly upright at one time of the year. And I just pictured that the first time he does this, it's overcast, because you need the sun's reflection. The next time, the stick falls over just before they were about to do their measurements. Anyway. I guess the other cruelty thing here. To calculate big G, the way that was done is you take a set of masses on a stand. So I got a stand here, and I have two masses where I know what those masses are. You take another mass dangling from a string, so I've got the two fixed like this, and I have another one dangling from a string, and then as I move this, we get to see how this reacts to it. And based upon, so the string, the fiber here is going to twist, and as it twists, you know how much force it takes to twist it, and so you can figure out the force based upon how the angle that it moves through. So the cruelty joke is that you have to set up and somebody walks into the room, causing a breeze, and the thing just sort of starts waving around. Now, it is in a box, so a truck goes by. The tediousness of that experiment. Probably, I think perhaps one of the two most tedious experiments in all of physics. The other one we would cover at the end of 152. There's time. And all of you have a wonderful afternoon, and probably have a good spring break. And Giovanni, I'm seeing you tomorrow.